Now we're going to talk about the structure of space and time, both in pre-relativity physics, which is the intuitive structure we all learn about just by living in the world, and in relativistic physics, which is the actual structure of space-time as far as we can tell. So pre-relativity physics, we think of space-time in the following way. So we can have a convention in this course, which is that time goes up. That is the universal convention. Okay, so when I draw space-time diagrams, time is always going to go up on the page. And space will either, if it's one dimension, it'll be, only out to the right. And if we want to show more dimensions, we can have another axis here, but we can't fit the third spatial dimension. So usually 2 is enough. Okay, so this is x and y, and there's another z dimension as well. All right. Now, in pre-relativity physics, we think of space as foliated, space-time as foliated by little flat planes. What are these flat planes? Well, this is t equals 1 second. It's an instant of time, right? So we think of this as being a nice flat plane for every instant of time. That was t equals 1 second. This one, I don't know, t equals 0.5 seconds, etc. So there's a whole stack of sheets of paper stacked on top of each other, and each one is an instant of time. Okay? And so we could have 2 events. An event is just a point in space at a moment in time. So event is just give t, x, y, z. So snapping my fingers is an event, but I am not an event because I persist through time. And a big extended blob is not an event because it persists through space. Okay, so the idealization of exactly one point in space and exactly one point in time is an event. And we would say that 2 events, A and B, are simultaneous. Simultaneous if, well, the time of A equals the time of B. Geometrically, they lie on this slice. And that's not a notion that anybody thought to question until around the turn of the 20th century. It just seemed obvious that there was this notion of time t. Everyone would agree on it, and we know what it means for 2 events to be simultaneous. Okay? Now, if we focus on a particular time slice, for each time slice, say this is now. So let's redefine this. Let's say this particular time slice is described by, that's just the instant of time now. There's a notion of the present. So if we pick that as the present, then anything with t coordinate less than it is the past, and anything with t coordinate greater than it is the future. And so you're going from the past to the future. Universally across all of space, they're separated by a flat plane. So that's the geometry of space-time in pre-relativity physics. Okay? Now, let's talk about the structure of space and time in relativistic physics. So the diagram is the same. We want well, not completely the same. The axes are the same. We're going to have 2 space axes, and time is going to go up, as always. But now, there isn't a universal notion of simultaneity. There isn't a structure, future, past, and present, that is universal. Everything depends on the event. So we have some event here, and the structure is what we call a light cone. So I'm going to draw, that's supposed to be 45 degrees, and like that. So light, because we set the speed of light to 1, this is a very important point, light rays are at 45-degree angles. Okay, so these are supposed to be light rays. And I'm going to imagine the light ray could be coming in any direction, including out of the board. And so we get not just a little x here, but we get a cone. All right? And in 3 dimensions, this represents a spherically expanding pulse of light. It's like a sphere moving out at light speed, as if you emitted a flash of light and all those photons went out isotropically. In 2 dimensions, that looks like a cone represented like this, and so that is called the light cone of the event P. Okay? Let's emphasize that by writing the event P. All right? And then inside the light cone, this is the future of P. This is the past of P. And everything else is, we're going to say, causally disconnected. Now, why do I say that? That's because of a property of the universe, which, again, physicists were dragged kicking and screaming to. They didn't just say, oh, it must be so. Experiments, in effect, proved it so. The property of the universe is that nothing can go faster than light. Okay? So, no signal, certainly no information, can go faster than light. And so, based on that, that's why we only call things that are reachable by a signal going slower than light to be the future of P. All right? For example, it would definitely not be in the future of P in any meaningful sense if you were out here. Because to get there, you'd have to draw a line that was more horizontal than vertical. Okay, not 45 degrees. So this line, this would be faster than light. Okay, and same with this one. Anything out in this region, not in the future light cone or the past light cone, would be faster than light propagation. That can't happen. So these 2 events simply can't talk to each other. And in fact, you'll show on the homework that you can always find a frame where these 2 events are considered simultaneous. And we'll also talk about how you could find a frame where this one down here is considered before this one up here. You can find another frame where this one down here is considered after up here. They're causally disconnected. One shouldn't be thought in the future or past of the other. Okay? The notion of future and past that's useful is when you can influence something. Then you'd say that something is in the future. Or if you can be influenced by something, you'd say it's in the past. So for example, this event here in red, I can draw a straight line which represents a slower than light because it's more vertical than horizontal. It's more time is elapsing than space in these units where equal time and space elapsed is light speed. And so that means you can send signal from, let's call this event A to P. So it's causally connected. And similarly, if we put an event up here, this one, let's call this B. So you can send signals from P to B. Okay? And so that's the relevant notion of future and past in special relativity, and also locally near a point in general relativity. Now over here, we said that A and B were simultaneous if Ti equals Tb. Now, what about in relativity? Well, there is no universal notion of simultaneity, or if you like, there's no observer independent. Groups of observers can get together and make conventions about what's considered simultaneous. That's something that's an inertial frame or a Lorentz frame that we'll talk about it. But in terms of the space-time structure itself, in relativistic physics, there's just no notion of simultaneous. It's replaced by this whole region outside the light cone where it's causally disconnected. And in the jargon, the region outside the light cone is called space-like relative to P, and the jargon inside the light cone is called time-like relative to P. Past or future. You could say it's in the past or in the future, or the interval from A to P is time-like. Okay, now let's express these ideas mathematically. So I need to introduce a notion of an inertial frame. And an inertial frame can be formally constructed by doing the following funny procedure. You imagine sitting in a room or something, and you put a clock in a sort of mesh grid, 3D grid, one clock at each vertex filling the room, floor to ceiling, wall to wall. Okay? And all these clocks have to be unaccelerated. Okay? So you got to have accelerometers to make sure that you're not secretly accelerating. Okay? And so imagine taking two clocks that are next to each other, and I'm drawing these vertical lines because time goes up, and if they're not accelerated, they could be represented as a straight line. Okay? So unaccelerated clock number 1 and number 2. Okay? So far, so good. We know how to put things equal distances apart. I don't have to explain what's meant by that in the special relativity course. But we do have to worry about time, and how do we in particular make sure these clocks are all synchronized? If you were just doing this in a room, looking at them, you'd just kind of watch them tick. But if you imagine trying to construct this over a huge region, well, when the clocks get far enough apart, you have to contend with the fact that light takes a finite time to travel there. And what you see is not exactly what the clocks are doing right then, in any sense. So there's a simple procedure that you can use, which is you bounce light from one to the other. So you imagine I want to synchronize these clocks. What I do is I send a signal, so 45 degrees. I bounce it off a mirror. And I declare that if this is time t1 and this is time t2, then the time that intersected better be exactly between them. Okay? And so I repeat this clock synchronization for every point in space. And what this defines is what we're going to call an inertial frame. Okay? Clocks like this at a grid x, y, and z synchronized. Now, I'm not going to derive any of this. You can go back to special relativity books to see how physicists arrived at these ideas. But the claim is that this all-important space-time interval is the same in every inertial frame. Okay, so this thing, delta s squared, which is calculated as minus delta t squared plus delta x squared. Let's put the delta y and the delta z. Okay, in any inertial frame, which by convention we denote as t, x, y, z. Now, I'm requiring that we use Cartesian coordinates x, y, and z as part of my definition of an inertial frame. When we get to general relativity, we're going to relax all this special frame stuff and so on. But for now, it's most convenient to introduce the ideas this way. All right? Now, we talked about space-like and time-like intervals, and now we can be a little more quantitative. We said space-like intervals are one where a signal could not reach from one point to the other, one event to the other, because it doesn't have enough time. It'd have to be going faster than light. And so you can see that a space-like interval is one where the spatial part is bigger than the time part. So the plus sign here overwhelms the minus sign in front of the time part. And so delta s squared greater than 0 is space-like. Okay? So delta s squared involves the straight line between two events. So PB, for example, write that up here, delta s squared from P in the middle to B up top. Let's write a little more clearly, delta s PB squared, that's going to be a time-like interval. So that's going to be negative. So let me include the time-like case here as well. So delta s squared is less than 0 is time-like. And let me do the space-like one over here. So for example, if this is c, then delta s p c squared is going to be positive because it's space-like. And the last case is everything on the light cone, where delta s squared is exactly equal to 0. And the most natural name for that is light-like, but it's not very common. Usually we say null. So as a matter of jargon, it's really time-like, space-like, null. Okay, and I want to emphasize these are properties of events, two events, and the straight line between them. The claim is you can calculate this using this formula in any inertial frame, and you'll always agree. Now let's think about what this thing means. What is the physical interpretation? Okay. Now, when we do physical interpretation, actually, the easiest thing to talk about is going to be the time-like case. All right. Light-like is interesting but subtle because it's always zero, so it's hard to say exactly what it means. And when we do GR, we'll talk more about thinking about light-like intervals in terms of something called the affine parameter, but that's for later. And space-like just doesn't come up that much because you'd have to send a signal faster than light, and it doesn't happen. So space-like is kind of the generalization of instantaneous distance that you have in Newtonian, but instantaneous distance is just not a very useful concept in a world where there's no notion of simultaneity, okay? So space-like doesn't come up as much, but time-like does, okay? And that's because for time-like, the interpretation is, and I'll first assert this, and then we'll check why. So if time-like, then this thing, which I'm going to write as square root of minus delta s squared, right? So this thing is just a positive number because delta s squared is negative for time-like. And so we make it positive by multiplying by a negative sign. Then we take the square root. Then this thing is the lapse of time on a clock moving from A to B. So I'll write this explicitly, delta s squared AB. And I'll draw an event A, and I'll draw a time-like separated event B, and I'll draw the straight line, and I'll put a clock. Okay, so this is a very physical thing. It's very clear. Experiments have been done. They put clocks on airplanes and tested all this stuff. And indeed, this is the thing you have to calculate to find out how much time ticked on that clock in the airplane. So this is very important. And a lot of what we're going to do in special relativity and general relativity is going to be just computing lengths of time on clocks for various observers, because it's a very simple thing you can do that still has a lot of the interpretation issues that are fun and interesting and new about general relativity. So we're going to do this observable really a lot. Now, notice that all our lines have been straight, which corresponds to an observer, or for a time-like interval, an observer moving at some constant velocity less than the speed of light. But we don't have to restrict ourselves to straight lines, okay? Just like the Pythagorean theorem tells you about triangles, but you can use calculus to get lengths of straight lines, you can use calculus to get the clock lapses for time-like trajectories. So this is a fairly simple exercise, and we can get the answer quickly with a kind of abusive notation. And here's how we do it. So we imagine that we have some curved path. So now this is our accelerated observer. Notice it never went at a slope that was more horizontal than vertical, because that would be faster than light. So its slope always has to be more vertical than horizontal. And how would we get the length, calculus style? Well, we would sort of imagine approximating it with little triangles. We would draw a little triangle right here that, and we would say, okay, this thing here is delta t. This thing here is delta x. And that corresponds to a little bit of space-time interval delta s by this formula. And so we'd write delta s squared equals minus delta t squared plus delta x squared, and I'll drop y and z for now. But of course, as this gets smaller and smaller, in the typical cavalier physicist way, let's just change these deltas to d's to represent some sort of infinitesimally small thing. And now, the most convenient way to think about it in relativity is think about a parameterized curve. So instead of giving x as a function of t, let's give t as a function of some parameter lambda, and x as a function of the same parameter lambda. And now we can sort of get the parametrized formula by a little bit of sleight of hand. Let's first use the interpretation that over this little triangle, the lapse of time on the clock is minus the square root of ds squared. So let's call that d tau, little lapse of time. So d tau is the square root of minus ds squared. And then using the formula above, that's just the square root of dt squared minus dx squared. And now I can use my parametrized curve idea where I just quote unquote multiply and divide by d lambda. So I'm going to put some of that under the square root as dt d lambda squared minus dx d lambda squared. And then I'll put some of it outside. And now finally I am ready to integrate. And so this is going to depend on a whole path from A to B. All right. And it's just going to be the integral of the square root of dt d lambda squared minus dx d lambda squared d lambda. Okay? And so that's for some time-like path moving from event A to event B. And that formula really deserves a box. That is the most important formula for calculating observables, at least that we're going to talk about. Okay? If you want to know how much time elapses on a clock, write that clock's trajectory as t of lambda and x of lambda and do this integral, and you're done. Okay? Now, there's something called the twin paradox, which you may have heard of. The twin paradox is not a paradox. Paradoxes can be fun to think about when they're sort of deep and interesting. The twin paradox is a paradox only because for a lot of time, and in a lot of classes even today, people think about special relativity all the wrong way. They talk about slogans like moving clocks run slow and lengths are contracted, which are very confusing slogans with extremely precise and confusing meanings, and then they run into contradictions. Okay? But here's what people call the twin paradox. They imagine one twin stays here. So let's say that's Ashley. So Ashley stays on Earth. Another twin goes out for a while and then decides to come home. So let's say that's Mary Kate. Okay, and what's supposed to be a paradox is that the length of time elapsed on Ashley's clock is different from the length of time elapsed on Mary Kate's clock. But that's obvious because this is path dependent, right? There's no way this integral is going to be the same. It's two totally different paths from A to B. Okay? So sometimes this is called twin paradox, but there's really no paradox. There's really nothing to say about it. And in fact, if you've never seen the twin paradox before, you probably think I'm crazy. And when I've taught this course to people who haven't seen it before, they really do think I'm crazy. They don't know why I'm making a big deal out of this. And indeed, there isn't a big deal. It's just the space-time analog of length of curve for time-like curves is the time elapsed. And of course, the length depends on the curve, right? And so the time elapsed depends on the curve. Now, in Euclidean geometry, this curved one, Mary Kate, is a longer curve on the page, okay? But we're doing so-called Lorentzian geometry with this minus sign crucially in there. And so it turns out that the straight line, whereas in Euclidean geometry that would be the shortest path, in Lorentzian geometry it's the longest time. Okay, so in fact, tau Ashley is greater than tau Mary Kate. All right? So Ashley is older. Mary Kate managed to be younger than her twin by traveling for a while. Okay? So it's not a paradox, but it's a pretty cool effect. And again, this sort of thing has been tested directly, indirectly by various experiments confirming special relativity, but also directly by, flying clocks around. And it really works exactly as this formula would predict.